Okay, it's 8 o'clock. Good morning, everybody. Okay, well, I got started grading all the exams yesterday. I've almost finished the exams for my other class, and I will finish those today. And then I will start yours. I will have yours back to you by Friday. Okay. By Friday, maybe Friday night, but by Friday, I'll finish them one way or the other. It takes me so long. Normally, grading a set of exams would be 3-4 hours maybe. But it's the file management that I have to do with downloading your files, grading them on the computer, and then saving them and then getting them back to you. It takes a long time. So, well, it is what it is. We're all living through this stupid pandemic and doing the best we can. Okay, so remember, you do have homework due Friday, and it has been posted on Blackboard. And I do continue every day posting the notes and the class recordings for you. Does anybody have any questions before we get started? No? Okay. Then I'm going to share my screen. Oh, my iPad tells me I'm sharing my screen. Oh, good. Okay. Let's see. This is yours. All right. Okay. Well, we've been talking about integration now. We're pretty far into it. And one of the rules we have is that an antiderivative of x to the n power is x to the n plus 1 divided by n plus 1. That works fine as long as n is not equal to 1. So that brings up the question, what do you do when n is equal to minus 1? So in other words, what's an antiderivative of 1 over x, which is the same thing as x to the minus 1? 1 over x has domain all the real numbers except for 0, okay? So I'm going to make the following definition. We're going to define a function in terms of definite integrals. ln of x is equal to the definite integral from 1 to x of 1 over t dt for x greater than 0. This is how we are defining this function. In other words, we're giving the antiderivative of this thing a name, okay? We're giving it a name. It's ln of x, and that stands for, okay, natural logarithm. And we'll be talking about what that means in the next couple of days. But okay, let's try to get a feel for this function. And I've graphed 1 over t here. And notice in my definition, my bottom number is 1. So, okay, so what would be ln of 1? Be the integral from 1 to 1 of 1 over, can't use, I don't want to use an X there because it's,
1.
yeah, okay, just a minute. uh, uh, uh. All right, there. I screwed up. Okay. Okay, the integral from 1 to 1 of 1 over t dt, what's it equal to?
It would be equal to 1.
How about 0? Because, okay, 1 to 1. Notice that the endpoints are the same. So essentially, that integral's taking the area of that vertical line segment. Does that make sense, Mr. Levy?
Yes, ma'am. Sorry.
Okay. Oh, no. Thank you for answering. I appreciate it. Okay. Well, what's ln of 2? Well, it's not so easy to figure out exactly. But what does ln of 2 represent? Okay, so this is a definite integral from 1 to 2 of 1 over t dt. Oh, yeah, I was going to say something else here. This is one of your properties of integrals. Right, we had this one that said the integral from a to a of f of x dx is 0. And also, since that 1 over t is non-negative, it would represent the area of that little vertical line segment. ln of 2, though, that would represent the area of the region from 1 to 2 under the curve. I'm going to color it in. Oops, I want this. Okay. Try not to go out of the lines. So, yeah, ln of 2 represents the area of that yellow region. So, well, in particular, it's a positive number. Okay, somebody just entered the waiting room. Let me let them in. It's somebody else. Yeah, it's an area. So, well, it's positive. It's positive. Well, let's see if we can get some kind of an approximation. Actually, I think I gave you this, well, a Riemann sum involving this function for one of your homework problems. So you're going to be approximating some of these numbers too. Somebody else entered. Well, let's see. How could I get an approximation? Well, there are lots of ways. A Riemann sum would do it for sure. But let's just do something crude here. The yellow region contains this rectangle I just drew. Okay, and this point right there, that vertex has coordinates 2, 1/2. What's the area of that rectangle? I call it the black rectangle.
It would be 1/2 times 1, which is equal to 1/2.
Yes, thank you. It's 1/2. Okay, well, the yellow region contains that rectangle, so that means that 1/2 is less than ln of 2. Okay, and okay, Mr. Levy, this is something you suggested doing a while back. What if I make a triangle there? So that would now the rectangle plus that triangle, now that contains the yellow region. So, well, the area of that triangle I just drew, that's 1/2 base times height, okay? And this point here is 1, 1. Okay. Okay, so, yeah, so this side has length 1/2, and the base is length 1. So the area of the triangle, 1/2 times base times height would be 1/2 times 1/2 times 1, which would be 1/4. So the area of the triangle union the rectangle, so both together, would be 1/2 plus 1/4 is 3/4. And since since this thing, this is a trapezoid, I guess, that trapezoid contains the yellow region. It has area bigger than the natural log of 2. Okay. So 3/4 is bigger than the natural log of 2. So that means then that we can know at least that 1/2 is smaller than the natural log of 2 is smaller than 3/4. Well, I think that the actual value is something like 0.69 something. Not absolutely sure about that. But you could get better and better approximations, and you're going to get some approximations of something like this for a homework problem. Well, let's see. I've got so much stuff on that picture. Maybe I'll do another picture now. Let's see. 1, 2, 3. 1, 2. 1, 1. 1, 1/2, 1, 1/3, and 1, 1/4. Here's 1/t again. If I look at the integral from 1 to 3 of 1/t dt, well, that would be ln of 3. Okay. Well, again, it's not that easy to figure out exactly what that number is, but we know something about it. Let's see. Let me do this first. We just got or just talked about the area of this region. That was ln of 2. Ln of 3, well, you're going to add some more stuff, right? I'm going to color it this color. So ln of 3 would be the yellow plus this little green region. Well, I don't know exactly what ln of 3 is equal to, but I do know that ln of 2 must be smaller than ln of 3. In fact, if I take 1 less than x less than y, to that's enough maybe. I'll put one more on there. Okay, there's 1 over t again. If I take, there's 1, and if I take x here and say y there, then ln of x is the integral from 1 to x of 1 over t dt. And let's shade that region in. That's an area. Oh, I don't want that. Let's have the nice minty green. Okay, so ln of x is the area of the green region. And ln of y, okay, well, ln of y, that's going to be a region that contains the green region. Let's see, that's shade that. Oh, here's y. There's y. Okay, so let's see if I can shade that in. Make that color. Okay. So ln of y is going to be, well, the green plus that sort of, I don't know what that color is, the yellowish region. Okay. Ln of y would be the integral from 1 to y of 1 over t dt. And that is the area of the green plus the yellow region. So ln of y is bigger than ln of x. Because the green plus the yellow region contains the green region. So far we know that if 1 is less than x is less than y, then ln of 1, which is 0, is less than ln of x is less than ln of y. Okay, so it looks like this function is increasing. But I haven't, let's see, in my definition, I just said that x had to be greater than 0. Pretty clearly, I cannot let x equal to 0, because 0, okay, well, my function 1 over t is not defined at 1 over 0. And if I define my integral this way, x is the endpoint of an interval in the domain of 1 over t. So x cannot be 0. But it can be a number between 0 and 1. What happens then? So I'm going to draw another picture, another graph. One half, 2. That's 2. Oh, nope, that's there. And my scale, that's there. That's there. Okay, so my curve, 1 over t, looks like this. And I'm going to be talking about, What happens when x is less than 1, but still positive? Well, let's look at x equal to a half first, okay? That's a number that's less than 1. ln of 1/2, by our definition, is the integral from 1 to a half of 1 over t dt. Okay, what does that integral represent? Here's a half, and here's 1. Only the 1's bigger than the half. What do the properties of integrals say that this definite integral is equal to? Anybody remember?
At the 0.1, it would be equal to 0.
If it were 1, it'd be 0. Okay. What happens when I flip endpoints on a definite integral? This was a couple of weeks back, I guess. Yeah. Probably a week before last, we talked about the properties of integrals, but this was one of them. If you have the integral from a to b of f, and that means this function, well, we were assuming the function f was continuous on the closed interval from a to b, okay? But we also said you could flip the endpoints, and the definition of integral still made sense, but it put a minus sign in front of it. You remember that? That's, again, okay. Again, I'm using a property of integrals. Yeah, all those properties, we talked about them, and then it's kind of easy to forget. But here's one. You can always come back to them. Always come back. Because once it's a property forever and for everything. Yeah, in mathematics, I love mathematics, but the rules are the rules, and you must not break the rules. But that doesn't mean there's not a lot of room for creativity within those rules. And once you know them, you can pull out and use any one you need, as long as you use it correctly. So here's one of our rules. This is a property of integrals. And okay, since there are numbers on the endpoints, these are definite integrals. So this is equal to minus the integral from a half to 1 of 1 over t dt. All right. And then now 1/2 comes before 1. 1/2 is less than 1. So it's the usual order of the endpoints. And the integral from 1/2 to 1 of 1 over t, that's an area of a region. Okay, I'm going to color it. That's better. I'll use that. So, yeah, okay. Let's see if I can keep it with my picture. The integral from a half to 1 of 1 over t dt is the area of the yellow region. Okay. And that means that the integral, that ln of a half is by definition the integral from 1 to a half, 1 over t dt. And that's equal to minus the integral from 1/2 to 1 of 1 over t dt. So it's minus that area, minus the area of the yellow region. Okay, so ln of a half is negative. That kind of makes sense when you think about, okay, ln of 1 is 0. Ln of x is positive for x greater than 1. Maybe it kind of makes sense that when you go to numbers that are between 0 and 1, ln of those numbers is negative. In fact, okay, that's true. So if 0 is less than x is less than 1, let me do no more arbitrary. Well, okay. Say I put x right there. Okay. Again, for such an x, okay, it's positive but less than 1, the definition says ln of x is equal to the integral from 1 to x of 1 over t dt. But x is less than 1. And that means in the integral, my lower endpoint is bigger than my upper endpoint. Okay, so this is minus the integral from x to 1 of 1 over t dt. And that integral, the integral from x to 1 of 1 over t dt, represents an area. So this is minus an area. And okay, the region involved here, okay, say this is my x right here. Okay, the region, I'll color it. Let's see, what color shall I make it?
Do green.
Do green? Okay, all right, I'll do green. There. All right, so that integral, okay, the integral from 1 to x is going to be minus the area of that green region. Okay, so we know something about this function. In fact, let's see. If I have 0 less than x less than y less than 1, okay, then the integral from x to 1, so that's upside down, as far as the definition goes. In terms of the order of the numbers, it's not. The integral from x to 1 of 1 over t dt is an area of a region. The integral from y to 1 of 1 over t dt is the area of a region. The integral from x to 1 contains, okay, so this region contains this region. And that means that this number, okay, I said that was less. That's not true, it's bigger. Okay. Yeah. From x to 1, let me put a picture. Okay. So let's see.
Dr. Kennedy?
Yeah.
So basically, in this here problem that we're looking at right now, that's just from 1 to half that we're talking about, right?
Okay, let me erase that 1/2. Okay. So I erased everything. All right, let me put it all back. 1/2 was just easy to look at. But right now, okay, we're looking at, suppose I've got 2 numbers less than 1. Okay. So there's X and there's Y. Then let me just come down here and do another picture. Okay, so I don't really need it that much, do I? Because we're looking at 2 numbers less than 1. Here's 1, and suppose there's X and there's Y. Then the integral from X to 1 over t dt. Okay, that's the area of a region, and let me draw the region. It'd be this one, and let's color that region. Okay, I'm coloring it green. You did a great job there. Okay, so that is the area of the green region. And then the integral from y to 1 of 1 over t dt. Well, that's a smaller region, right? There's y, and then the integral from y to 1 would be that area right there. So that's the black region. That's equal to the area of the black region. So yeah, so this region is a subset of that region. That means that this area is less than that area. Oh, and I'm pointing with my pencil and you can't see any of that. Okay, so let's write that down. The integral from y to 1 of 1 over t dt is less than the integral from x to 1 of 1 over t dt. Because those represent regions and one's a subset of the other.
So I know you're just explaining it right now, but whenever we are going to see this on like assignments, will we be given a graph and integrals, and then we'll determine who's bigger than who?
A little bit for this, not for this week's, for probably next week's assignment. Every time you encounter a new idea, as a mathematician, and mathematicians have to do this all the time. Yeah, part of my job is discovering new mathematics. So you're always learning new things and dealing with new things. What's the first thing you do when you encounter something new? I try to understand it. Yeah, explore. That's what we're doing right now. Okay.
Gotcha.
And anytime you do that, you start building an intuition in your mind and a feeling for what you're dealing with. And once you understand, you begin to understand, you can keep growing what you understand. And that's what we're doing right now.
Okay.
Gotcha. This whole idea of defining a function in terms of definite integrals, well, it just looks a little strange at first.
Well, right? So we're basically given a function, and then these integrals are just sections of the function, right? That's basically it.
Yeah, we're kind of thinking about what that means when you define a function in this way. Okay. Yeah, when we're interpreting it in terms of areas of regions, that's exactly what we're doing.
Okay, gotcha.
Okay.
Now
All
I'm
right.
on track.
Okay. Okay, but that's a good question to ask. Let's see, I forgot where I was. Right. So we've established that this integral is a smaller number than that. The integral from y to 1, this, okay. Integral from y to 1 of 1 over t dt is a smaller number than the integral from x to 1 of 1 over t dt. Because the area of the black region is contained, well, it's got to be less than the area of the green region because the black region is a subset of the green region. Okay, but what does that say about our logs and our new function? Well, that says minus, okay, that says minus the integral from y to 1 over t dt. I'm just putting a minus in front of both these numbers. You multiply through by minus, it flips the order of the inequality. Right? And now this number is ln of y. Maybe just put that on another line there. Okay, this number is ln of y. And this number is ln of x. Because ln of y is by definition the integral from 1 to y of 1 over t dt. But that's equal to minus, if I flip the endpoints, the integral from y to 1 of 1 over t dt. And ln of x is the integral from 1 to x of 1 over t dt. That's the same thing as the integral, then minus the integral from x to 1 of 1 over t. Okay, so ln of y is greater than ln of x, or in other words, just looking at two numbers less than 1 but positive, we still have this inequality. And that means that for any x and y, okay, if x is less than y is greater than 0, period. So we looked at x and y bigger than 1 up above. We've shown that ln of x is less than ln of y. And that means this new function is increasing on the positive reals. Yeah, the domain of this function is the positive reals. It's an increasing function. Okay. Are you all still there?
Yes, ma'am.
Okay, good. Need to check every now and then. We can start drawing a graph of this new function. Okay, we know that, okay, very little. ln of 1 is 0 because it is the integral from 1 to 1 of 1 over t dt. We know if x is less than y is greater than 0, ln of x is less than ln of y. We know that if x is greater than 1, ln of x is positive, and if 0 is less than x is less than 1, ln of x is actually negative. That's not legible. Okay, so I'm going to start a rough sketch. It really helps me if I can see things. I know that that's one right there. ln of 1 is 0. ln of 2, we said it was between 1/2 and 4 and 3/4. So we know that for sure. I'll put a point there. ln of minus 1/2. Well, it's negative. ln of 1/2 rather is negative. We'll learn something about that in a minute. Okay, so ln, it's increasing. This is the beginnings of a picture of ln of x.
Could you scroll down a little bit so I can see the rest of your writing?
Sure. Okay. Well, tell me this. We have ln of x. What's the derivative of this function?
Would it be a exponential function?
No. Okay, we're going to get to exponential shortly. Okay. Yeah, they're coming. Okay, let me tell you this hint. Remember the fundamental theorem of calculus? Again, that was seems like forever ago now. Yeah, because last week, I guess we were, well, maybe it's been Monday last week. I think it was Monday or Tuesday. Okay. Okay. If you have a function defined in this peculiar way, okay, this was any number, didn't have to be 1. A to x of, oops, cannot put an x there because x represents the endpoint of an interval. If you define a function in this way, we said that f prime of x was equal to g of x. That was part 1 of the fundamental theorem. So yeah, since I'm defining this function in terms of the antiderivative of 1 over t, the derivative of this function is basically, well, it's not 1 over t, it's 1 over x. Okay. In fact, okay, this, gosh, okay, we've talked about the definition of a definite integral. That was a fairly complicated definition. So you have to absorb all of that. But when you write this, okay. When you define a function this way, t always represents a number between 1 and x. That's why you can never put Well, whatever this letter is cannot be the letter inside the integral. Okay. It can't be the letter after D. Because then it would represent two things. T is trying to represent all the numbers between 1 and x. 1 and x are endpoints of that interval. And of course, as x changes, so does the interval. But the fundamental theorem of calculus says that the derivative of ln of x then is just 1 over x. Any questions? One of the nice things about this is that it makes you think about all those properties we talked about and makes you think about the fundamental theorem of calculus. Okay.
So you basically said that the derivative of ln of x is 1 over x
Yes.
because t is trying to represent everything in between 1 and x.
It's because, well, okay. When I, let me, wait. No, that's not why. Anytime I write this. Okay. So this is a definite integral. That means that t represents numbers in between 1 and x.
Okay.
Okay. Now, well, we put another that's just from the definite integral thing. But now we're defining this to be this definite integral. Okay. So now I'm allowing x to vary over the positive numbers. And ln of x, I'm defining to be the integral from 1 to x of 1 over t dt. Yeah, there are two things to keep track of. We just started getting a picture of what this new function looks like. Okay. And we talked about it and got this picture from thinking about what these definite integrals look like. But there's also this other function, 1 over t. Well, there it is. Many times I've sketched it today. The integral, yeah, 1 over t is the other function. This function and this function are very much related. The derivative of ln of x is 1 over x, and that comes from the way we have defined ln of x and the fundamental theorem. So we already know what the derivative of this function is. And then again, so since the derivative of this new function is 1 over x, and x is greater than 0, so 1 over x is also greater than 0. That again says this function, this new function, is an increasing function. Because having a positive derivative means your function is an increasing function, right? If you have a positive derivative on the entire domain, then a function is increasing over the entire domain. Okay, well, what's the second derivative then? That would be the derivative of 1 over x. And now I can just write that down. That's minus x to the minus 2 is minus 1 over x squared. And remember, x must be greater than 0 here. But it can't be 0. X squared is always positive as long as x is not 0. But this number in particular is less than 0. And that's true for anything in the domain. So here we domain over there. The second derivative, so the second derivative of ln of x is negative. That says that this function is concave down. So since, let me write it this way. The second derivative of ln of x with respect to x is less than 0. The natural log of x is concave down on its entire domain, which is the positive numbers. And there again, that means that this picture we started drawing of this function, well, that looks like it's concave down. Okay. So far, so good. We still have questions. Well, what happens as x gets large without bound? I guess there are two possibilities. This function could level off, and that is have a horizontal asymptote, or it could increase forever, increase without bound. And also, we want to know what happens as we come into 0 from the right. That is the limit as x approaches 0 from the right. What happens to this function? Does it, well, do we have a vertical asymptote? Or does this sort of come in somewhere, come in towards this y-axis and never get below a certain point? So we want to know that. Well, how can we answer that? And what time is it? Oh, time to go. Yeah. Okay. I spent a lot of time today talking about this. And so we've discovered some things about this new function. We're going to do some more tomorrow. In particular, I'm going to show you that, okay, I call this a natural logarithm. A logarithm function, well, to be a logarithm function, the function must have certain algebraic properties. Tomorrow, I'm going to show you that this function has those algebraic properties, okay? And I'm going to show you that using its definition. I don't know. I love this stuff. When you're bringing the ideas together, okay, you're probably thinking, why is she spending so much time on this? There is a reason, okay? But anyway, okay, we'll say class is over and hang around if you have questions. Otherwise, I will see you tomorrow.
Have a good day.
You too.
Hey, Dr. Kennedy.
Yeah.
If